Hello and welcome to your stats notes. All right, so today we're going to be talking about transforming and combining random variables. Now, the transforming part is going to feel very familiar because we've basically already done it. The combining random variable part is going to be new. So we'll start by reviewing the transforming stuff, and then we'll get into the newer combining stuff. So this basically says, review from chapter 2, when you add or subtract a constant, you have to add or subtract that same constant to your measures of center, so mean and median, but it doesn't change the shape and it doesn't change the spread, so things like standard deviation and IQR. When you multiply or divide by a constant, all right, you multiply the mean and the median by the same amount. It still doesn't change the shape, but it does change the standard deviation and the IQR. All right, so we're going to apply these same rules to random variables. So if you add or subtract a constant from the data, the mean is shifted by the same amount. In the same direction. So what does that look like in terms of kind of like symbol or notation? So E for expected value. So the expected value of X, when you add or subtract a constant, is just whatever that expected value of X was by itself, plus or minus whatever constant you just added. All right, so pretty much exactly what we did before. If you're adding 5 to everything, the expected value goes up by 5. If you subtract 10 from everything, the expected value goes down by 10. And then on the other side, the variance and standard deviation. So remember, the variance is just the standard deviation before you take the square root, remain unchanged. So the variance or the standard deviation of X plus or minus a constant, X plus or minus a constant, is just the original variance of X, the original standard deviation of X. The constant does not matter. So if you add 5 to everything, it doesn't change how spread out that data is. So the standard deviation and the variance stay the same. In contrast, when you multiply each value by a constant, the mean is multiplied by the same constant. The standard deviation is multiplied by the same constant. And are you asking yourself, Mr. Boner, are you really making me write the same exact thing 3 times in a row? Good luck. I'm not, because the variance is multiplied by the constant squared. All right, so again, if we're kind of doing this in like a notation format, if you're doing the expected value where A is your constant and you're multiplying it by X, it's the same as just taking the expected value of X and multiplying it by A. All right, if you're trying to find the standard deviation of a random variable X after it's been multiplied by a constant, it's just that constant times the standard deviation of your original x. And then last but not least, if you're trying to find the variance of a constant times a random variable, it's that constant squared times the variance of the original variable. All right. So we didn't really deal with the variance a whole lot back in chapter 2, but all this other stuff should be familiar. All right. Yes, it's different language because we're talking about random variables here, but the concept is exactly the same. All right. If you add or subtract a constant, it only affects the mean. If you multiply or divide a constant, it affects both the mean and the standard deviation. All right, so let's just do a couple of problems to make sure we're on the same page, and then we'll get to the newer stuff. All right, heights. The report of the National Center for Health Statistics says that the height of 20-year-old men has a mean of 176.8 centimeters and a standard deviation of 7.2 centimeters. There are 2.5 centimeters in an inch. What are the mean and standard deviation in inches? All right, so effectively, the transformation that we're doing here is dividing by 2.5. All right, if we divide by 2.5, that's going to take our centimeter answer and turn it into inches. Now, because we're dividing by a constant, we're going to have to impact both the mean and the standard deviation. This is going to affect both of them. All right, so both the mean and the standard deviation need to be adjusted. Right? If we were adding a constant, we would have only adjusted the mean. But because we're dividing, we have to do both. So it's basically just the 176.8 divided by the 2.54. All right, so 176.8 divided by 2.54 equals 69.61. And then the same thing here, we have to divide the standard deviation. So 7.2 divided by 2.54. 7.2 divided by 2.54 is 2.83. All right. And now those are both in inches. So that's in inches. That's in inches as well. All right, so when you multiply or divide by a constant, it affects both of those values. All right, let's take a look at number 2. In a process for manufacturing glassware, glass stems are sealed by heating them in a flame. The temperature of the flame varies a bit. Here's the probability model of the temperature X measured in degrees Celsius. All right, so they're giving this to us as a discrete random variable. And part A says find the mean and standard deviation. All right. So when they're giving us one of these tables, again, all of these values are going to go into L1. All of these values are going to go into L2. And then we're going to want one variable stats with L2 as our frequency list. All right. Now, I've already gone ahead and typed those in there. So there's all my payouts in L1. There's all my probabilities in L2. So when I go to one variable stats, I make sure that the frequency list is set to L2. Then I can hit calculate. And I can find that my expected value or my mean is 5502. And again, my standard deviation, which there is no sample standard deviation here, so it's the population standard deviation that we're using. I'm going to round that just to 58.15. All right, so those are the two values that I'm reading from my calculator there. Now, part B says the target temperature is 5,500. So what are the mean and standard deviation of the number of degrees off target? So how far did we miss the mark? All right, so this is subtracting by 5,500. And again, because that's a constant, this one is only going to impact the mean. All right, the standard deviation stays exactly the same. All right, the standard deviation is still going to be the same 58.15 that it was up above. That one's not impacted. The mean, however, is impacted. All right, and we were we're subtracting what, 5,500, so it's basically the 5,502 minus 5,500, and we're getting a new mean of 2. All right, so standard deviation stays the same. Our mean does go down to 2. Part C, the manager asks for these results in degrees Fahrenheit. The conversion of x into degrees Fahrenheit is given by y equals 9/5 x plus 32. So we're going to take these results that we just got here and convert them to degrees Fahrenheit. Now, converting these results into degrees Fahrenheit is a series of 2 transformations. We are multiplying by 9/5, and then we are adding a 32. This one is multiplying by a constant. This is going to affect both our mean and our standard deviation. All right, both are affected when we're multiplying by a constant. So our new mean is going to be this 2 times 9/5. Our new standard deviation is going to be this 58.15 times 9/5. Right? Both of these are impacted because we're multiplying by a constant. So 9/5 times 2 becomes 18/5, which is basically 3.6. Right, and then the other one I can't do in my head. So 58.15 times 9/5, 104.67. Right, that's the first transformation. However, there's a second transformation. All right, now the second transformation is adding a constant. So this only impacts the mean. So we're going to take this one only impacts the mean. So we're going to take this 3.6 and we're going to add 32 to it. All right, and that's going to give us a final answer of 35.6. All right, this is our mean. Our standard deviation, we're done with. All right, we don't have to change anything on our standard deviation, all right, because this does not impact it. All right, there's no impact on this right here. So this can stay the same, and this just becomes our new standard deviation. All right, but you just have to see this as, okay, this is 2 separate transformations. This part affects both. This part only affects the mean. All right, and that's where my 2 answers are coming from. So that's the stuff that should be familiar. All right, that's the stuff that you should be like, okay, yep, that rings a bell. We did this before. This is the new part. All right, and this is when you add together 2 random variables. All right, so this is not adding 2 constants. This is adding 2 random variables. So what happens when you do this? All right, so when it comes to the expected values, you just add the expected values. All right, so this is the easy part of it. So if you want to know the expected value of x plus y, it's just the expected value of x plus the expected value of y. All right, that's the easy part. What happens when, what do you do with the standard deviation? Well, it turns out that you can't just add the standard deviations, and it's not that they stay the same like they did for constants. You have to add the variances. Now, most of the time, we don't actually work with variances. So the little note I'm going to put in here is if you are given the standard deviation, square it, which turns it back into a variance, then add them, because we can add the variances, then take the square root again. All right, and we'll see how this plays out in a problem. But that's the general idea. And again, it's the variance of x plus y equals the variance of x plus the variance of y. Now you might be asking yourself, all right, I'm confused. Like, why, when I'm adding a constant, does it not make a difference? Why, when I'm adding random variables, do I have to do this extra little step here? All right. Well, think about it this way. Pretend your random variable was rolling a die. All right. On one die, you could get 1, 2, 3, 4, 5, 6. All right. Now let's say I want to add that result to a second die. So on the second die, I could also get 1, 2, 3, 4, 5, and 6. When I add these together, I go from having a range of 1 to 6 to suddenly having a range of 2 to 12. So the range of my numbers has just gotten a lot bigger. I've gone from a range of 5, 6 minus 1, to a range of 10, 12 minus 2. So things are getting much more spread out. Contrast that to adding a constant. All right, let's just say I added 1 to each of these so that it went from 1 to 2, 2 to 3. Then my range would just be going from 2 to 7. All right, it wouldn't be any more spread out. It would still be a difference of 5 between the max and the min. So adding a constant doesn't change how much things are spread out. But when we have these two random variables, there's all sorts of different combinations. I could get 1 plus 1, I could get 1 plus 2, 1 plus 3, 1 plus 4, 1 plus 5, 1 plus 6, so on and so forth. Or I could get 6 plus 6, 6 plus 5, 6 plus 4. There's all sorts of different combinations that I can get, and that increases the spread of my data. All right, how exactly does it increase it? It increases it by adding the two variances together. All right, that gives you your new combined variance that represents the spread, in this example, from 2 to 12. All right, now let's talk about what happens when you subtract two random variables. All right, again, the first part is the easy part. We subtract the expected values. So the expected value of x minus y is still the expected value of x minus the expected value of y. Now, what happens to the standard deviation or the variance when we subtract two random variables? All right. Most kids' inclination is to say, oh, we probably just subtract the variances. Not actually, and I'll show you why in a second. We actually do the same exact thing. All right. We add the variances. Right? And this is the part that kids have a hard time remembering. But the variance of x minus y is actually the variance of x plus the variance of y. All right, and I'm going to show you why here in a second. So here I was adding these together. I was saying, okay, I could get 1 plus 1 and get 2. I could get 6 plus 6 and get 12. Let's pretend I was subtracting them. All right, if I was subtracting this, the most negative value I could get would be a negative 5. All right, 1 minus 6 would give me a negative 5. And then there's a couple of different ways I could get negative 4, and there are ways I could get negative 3, and there are ways I can get negative 2, and negative 1, and 0. And then if I started doing 6 minus 5, I could get a positive 1. 5 minus 4, a positive 1. There's a bunch of ways to get positive 1. There's a bunch of ways to get positive 2, 3, 4, all the way up to positive 5 when I'm doing 6 minus 1. So even though I'm subtracting these values, 1 minus 6, 1 minus 5, you can see the spread is increasing. And in fact, the spread is exactly the same as when I added them, right? When I added them, 12 to 2 was a range of 10. 12 minus 2 was 10, all right? When I subtracted them, I can go from 5 to negative 5, still a range of 10. So it didn't matter whether I added together all the different combinations of my random variables or whether I subtracted all the different combinations of my random variables. The values ended up equally spread out, which is why it doesn't matter whether you're subtracting or adding these random variables. The variances always get added. All right, so a little counterintuitive, but if you break it down and really think about it, you can see why it doesn't matter whether you're adding or subtracting random variables. You're getting the same spread from those two situations. Now, we don't have to worry about multiplying or dividing random variables. That's not something we're going to deal with in here. You just have to focus on adding and subtracting. And the note that we're going to add here is this only works if the random variables are independent. All right, if they're not independent, you can't do any of this and you just move on to the next problem, more or less. All right, so scores on the and this is referring to this part right here, this variance part. This only works if random variables are independent is referring to this variance part here. So let's actually look at a problem here. Scores on the mathematics part of the SAT college entrance exam in a recent year had a mean of 519 and a standard deviation of 115. Scores on the verbal part of the SAT had a mean of 507 and a standard deviation of 111. What is the mean of the total SAT score? All right, so we have a random variable. We could call that random variable M for math. All right, we have another random variable V for verbal. So this is basically saying, what's the expected value of M plus V, which we know is just the expected value of M plus the expected value of V. And I don't really want to overcomplicate this because all you're doing is taking this average and adding it to this average. So 519 plus 507 and getting 1026 as the mean total SAT score. Now, part B says if you can calculate the standard deviation of the total SAT score, do it. If not, explain clearly why you can't. All right. Now, here's where I would argue that these two measurements are not necessarily independent. Now, yes, there are kids that are really good at verbal and bad at math, and there are kids that are really good at math and bad at verbal. But for the most part, if I tell you that somebody got an 800 on their math, you probably expected them to do at least decent on their verbal. All right. If I told you somebody got, I don't even know how low they go. I don't think they go this low, but if I told you, oh, somebody got like a 100 on their math, you're probably like, yeah, they probably didn't do so hot on their verbal either, because I don't even think you can get a 100. So we can kind of see that these two are not necessarily independent. So in fact, we're not allowed to combine their variances. All right. Here, when I talked about the dice rolling example, these are independent. All right. So what I get here has no impact on what I get here. But if they're dependent and I get a 1 on the first roll, and that means I'm more likely to get like a 2 or a 3 or a 1 on the second roll, then it goofs up this whole thing that we just talked about. All right, it goofs up the probabilities here, it goofs up the likelihoods, which means this no longer applies, and it becomes much more involved to figure out what the combined variance would be. So in this case, we can't calculate the standard deviation. So math and verbal SAT scores are not independent. And if you want like a reason why they're not independent, kids that do well on one tend to do well on the other. All right, so we can't just combine these. Instead, we have to just say, oh, sorry, we're done. All right, there's your average, there's your mean SAT score. I can give you that, but I can't figure out the spread or the standard deviation because the two things aren't independent. Now, let's actually look at some calculations here. So it says, given the independent random variables with means and standard deviations as shown, find the mean and standard deviation of each of these. Okay, so we have a random variable x that has a mean of 80, a standard deviation of 12. We have a random variable y that has a mean of 12 and a standard deviation of 3. So this first one says, all right, what if you subtracted 20? What if you subtracted a constant? What would happen to the mean? What would happen to the standard deviation? All right, so we're going to put all of our means on the top. This is going to be our mean row, and we're going to put all of our standard deviations down below. Right. So when we're subtracting a constant, the mean is subtracted by that same constant, but the standard deviation, whoops, over here, the standard deviation is not affected by adding or subtracting a constant. Here, we're multiplying by a constant, right? So when we multiply by a constant, the mean is multiplied by the same constant, and the standard deviation is multiplied by the same constant. So both of those pieces are impacted. All right. Now, we're not adding a constant, we're adding a random variable. So we take those two means and we add them together, 80 plus 12, and we get 92. Now on this one, our standard deviations, we don't get to add the standard deviations, we get to add the variances. So what that means is I have to do 12 squared plus 3 squared. Now, when I do 12 squared plus 3 squared, that will give me the new variance, but I still want the standard deviation. So I'm going to take the square root of that value. And I always just kind of tell kids, it kind of looks like you're doing like Pythagorean theorem. It's like the old a squared plus b squared equals c squared problems, where you would like have to take the square root of both sides. It's kind of what it looks like. I mean, obviously it's not related, but it's sort of what it looks like. So 12 squared plus 3 squared. I should have just 153. And then I can take the square root of 153, and I get 12.37. All right, so my new standard deviation would be 12.37. Now, here, I'm subtracting the random variables. So I'm going to do the 80 minus 12. All right, that's the part that's pretty intuitive. But this calculation is going to apply to this and this. It's the same exact calculation. It doesn't matter whether I'm adding the random variables or subtracting the random variables. It's the same exact process for the reason that we talked about over here. So this is going to be 12.37 again. All right. And then last but not least, we'll have these problems where you're taking the same random variable and you're like adding it to itself. So here y is 12, so this just becomes 12 plus 12 or 24. And then the standard deviation is going to be 3 squared plus 3 squared. That's the variance. And then we have to take the square root of that, meaning we're basically taking the square root of 18, and we're getting 4.24. All right, but this chart is useful because it shows you the different scenarios. Subtracting a constant, multiplying by a constant, adding random variables, subtracting random variables, and then just showing the situation where you're just adding a random variable to itself. All right, so let's look at a couple more examples just to make sure that we're good with this. So what about continuous random variables? If two independent continuous random variables have normal models, so does their sum or difference, which is basically saying, you know, we can use NCDF, right? Because it's still going to be a normal curve. All right, so the design of electronic circuit calls for a 100 ohm resistor and a 250 ohm resistor connected in a series, so the resistance adds. The components are not perfectly uniform, so the actual resistance vary independently according to normal distributions. The resistance of a 100 ohm resistor has a mean of 100 ohms, but a standard deviation of 2.5 ohms, while that of a 250 ohm resistor has a mean of 250 and a standard deviation of 2.8. So basically saying like, yeah, you used a 100 ohm and a 250 ohm, but sometimes the parts are a little better, sometimes the parts are a little worse. And even though they average out to 100 ohms, they won't always be exactly that. Even though they average out to 250, they won't be exactly at that. So it says, what is the distribution of the total resistance of the two components used? So you can think of these as random variables. You can think of them as, okay, we've got my random variable X, which is the 100 ohm resistor, and we've got my random variable Y, which is the 250 ohm resistor. And what they're asking about is, all right, if we put these in sequence, what is X plus Y? All right, so the new expected value, or the new mean, is just going to be the 100 plus the 250 for a total of 350. The new standard deviation, we can't just add the standard deviations, we have to add the variances. So that's 2.5 squared plus 2.8 squared, but we still want the standard deviation, so we're going to take the square root of that result. So we've got 2.5 squared, whoops, plus 2.8 squared. And then we're going to take the square root of that and get 3.75, we'll say. So when we're looking at these two resistors together in sequence, their combined resistance is 350 ohms, but the combined standard deviation is now 3.75. So when it says, what is the probability that the total resistance lies between 345 and 355, that's where we can now use our NCDF. And we can say, all right, what are the odds of being between 345 and 355 when our mean is 350? and our new standard deviation is 3.75. So a way a lot of these problems are going to work is step 1 is finding your new standard deviation and mean. Step 2 is using that as part of an NCDF calculation. So NCDF 345 to 355 when the mean is 350 and the standard deviation is 3.75. And we get 0.8176. So that would be our final answer there. All right, so let's take a look at another one of these, just to kind of get comfortable with them. The diameter C of a randomly selected large drink cup follows a normal distribution with a mean of 3.96 and a standard deviation of 0.01. The diameter L of a random selected large lid follows a normal distribution with a mean of 3.98 and a standard deviation of 0.02. For a lid to fit on the cup, the value of L has to be bigger than the value of C, but not by more than 0.06 inches. What's the probability that a randomly selected large lid will fit on a randomly chosen large cup? All right, so we're basically doing a subtraction type situation here, and then we're limited to, the size that the difference is allowed to be. So again, the lid has to be bigger than the value of C, but not by more than 6 inches. So if we do the size of the lid minus the size of the cup, we need that to be less than or equal to 0.06. All right. Now, hopefully it goes without saying that we also need that to be bigger than 0. All right. So if the lid is smaller than the cup, it's also not going to fit on. All right. So the lid needs to be bigger than the cup, but not too big because then it won't fit. But it does have to be bigger because otherwise that won't fit either. It can either be too big or too small, and we're sort of limited to this range right here. And we want to find what's the probability that this ends up inside of this range. So we're looking at an NCDF from 0 to 0.06, but we have to figure out our mean and standard deviation. All right. So again, if we're trying to find the mean, I'm going to use the population mean here of L minus C, or even better, yeah, let's do it this way. If I want to know the expected value of L minus C, it's just the expected value of L minus the expected value of C. Well, we know the expected value or the mean of the lid is 3.98. We know the expected value of the cup is 3.96. So the expected difference between those two is going to be 0.02. All right, this is what we're using as our mean. So that's going to go right here inside of our NCDF. Now, if we want to know the standard deviation, that's where we're going to have to add the variances and then take the square root to get it back down to a standard deviation. All right, so if we're trying to find the standard deviation of L minus C, then what we're really doing is taking the variances, which is 0.01 squared. All right, the variance is just the standard deviation squared, plus 0.02 squared. And then we take the square root to get that back into a standard deviation. So we've got 0.01 squared plus 0.02 squared. All right, and then if we take the square root of that, we end up with 0.0224, we'll say. That's the standard deviation for L minus C, right? Again, there was the standard deviation for L, there was the standard deviation for C, there's the standard deviation of L minus C. All right, so right there is the standard deviation of L minus C. So that's what's going to go up here in the final part of our NCDF, 0.0224. So we're now saying, what's the probability that the difference between these two is somewhere between 0 and 0.06? We just head over to our calculator, 0.06 when the mean is 0.02 and the different standard deviation is 0.0224. And we get, what's that going to round up to? 0.770. So 0.7770. All right, but again, it's finding your new mean and standard deviation and then using those to, in an NCDF, to answer some sort of percentage or probability question. All right, now, before we end it for today, I always like to incorporate gambling, or at least try to incorporate gambling. So let's apply this to a gambling question. On a single $1 bet on a roulette wheel, the expected value of a spin is -5 cents with a standard deviation of $1. What a great deal. You've got $100 burning a hole in your pocket. Do you think you're better off making 100 $1 bets or one $100 bets? One $100 bet. Probably shouldn't be plural there because you're only making one bet at that point. Use your knowledge of random variables to compare the two situations. All right, so what we're really comparing is making a $100 bet, which is the equivalent of multiplying by 100, versus making $101 bets, which is the equivalent of adding together random variables over and over and over again 100 times. So we're either multiplying by 100 and putting it all into one big bet, or we're making lots of little bets, each of which represents a random variable. So we know that for a single bet, the expected value of x, or just e of x, you don't have the v there. So e of x is -0.05. And we know that the standard deviation of x is 1. Right? We can now use our transformations to answer these two questions. So in the multiply by 100 situation, right, we're multiplying by a constant. So the new expected value is just going to be -0.05 times 100. All right, and that's going to give us -5. All right, that would be our new expected value. So this is expected value. Our new standard deviation, because we're multiplying by a constant, is just that same thing, 1 times 100 for $100. So if we were to make a single $100 bet, on average, we would lose -$5, but the standard deviation would be 100, all right? Basically, you're going to get wild swings up or down because you're putting all your money on one bet. So when you win big, but when you lose big. All right, let's compare that situation to the situation where we're just adding them over and over and over and over again. So in this case, the expected value would be found by adding -0.05 over and over and over again until we did that 100 times. All right, so we would be adding together negative 0.05 100 times. Now, when we do that, we're actually going to get the same exact value. All right, it's still going to give us the negative 5 that we got up here. All right, what's going to be different is the standard deviation. All right, so the standard deviation is going to be found by taking all those standard deviations, squaring them, and adding them together. All right, so that would be 100 ones being squared and added together. Now, the nice thing about that is 1 squared is just 1, so I'm basically just adding 1 100 times. So this basically turns into the square root of 100, which means the standard deviation is 10. So what we're seeing here is when we make the big bet, we have a much higher standard deviation than when we make the small bet, which intuitively makes sense. All right. If you put all your money on one roll, you're either going to win big or you lose big. If you break it down into 100 different bets, you might win some, you might lose some. So on average, you're going to be much closer to this negative 5 than you are up here. All right. Up here, you're really not ever going to be a negative 5. You're either going to be down in the hole $100 or you're going to be winning a whole lot more. Up here, you might win some, you might lose some. So you are going to end up a lot closer to this negative 5. So even though two situations can have the same expected value, if they have different standard deviations, you can expect very different results. All right, here you expect to be way above or way below this negative 5. Here you expect to be pretty close to that negative 5. And that has very important sort of real world implications. So basically, this one has the same expected value, but much less variation. All right, so that wraps up these notes. Again, this first part should be pretty familiar. It's what we've already done. This new part, this is the part that generally gives students the most trouble. Just remembering that when you subtract, you're still adding these variances, and then remembering that you don't just get to add them, you don't just get to combine them. You do have to use sort of this, again, I call it like a Pythagorean theorem looking thing, where you're squaring the standard deviations to turn them in variances, adding them, and then taking the square root to turn them back. And a lot of times we're going to use these as part of like an NCDF, where these two numbers are coming from all that stuff we just talked about. And then you're doing the NCDF like we've done, for a long time now. All right. And it doesn't matter whether you're adding or subtracting, you're still adding when it comes to finding out the new standard deviation. All right. So hope this was helpful. If you have any questions, just let me know. We'll go from there. All right. Bye.